Hello, I'm Stephen Sharp, and welcome to my presentation for the final project for AERO 465. So for this project, I wanted to recreate one of the examples listed in the instructions of a device that predicts the speed of sound using atmospheric properties and then actually measures the speed of sound using an ultrasonic sensor. My only problem is that I didn't have a barometer or pressure sensor, only a temperature sensor. So while I can still predict the speed of sound using the equation square root gamma TR, I still need an additional device in order to complete the project specifications. So I figured I'd use that additional device for a different purpose, to make the concept a little more interesting by warning the user if the environment they're using the device in becomes too dangerous for humans. The sensors that I used in my project consisted of an ultrasonic sensor, a liquid crystal display, a temperature and humidity sensor, a gas sensor, and then there were two other devices being a passive buzzer and a DC fan. All of these devices are hooked up to the Arduino's 5-volt power supply with the exception of the backlight for the liquid crystal display, which is only 3.3 volts. Usually you're supposed to use a potentiometer to adjust the contrast of the liquid crystal display, but instead I just put a 1 kilo ohm resistor going from the pin to ground because I don't have a potentiometer. You can also see there's another potentiometer going from the backlight power supply to the liquid crystal display backlight, which is there to prevent overcurrent of the backlight. It's also interesting to note that these sensors filled up all of the digital pin slots with the exception of pin slot 7, and only one of the analog pin slots. While the liquid crystal display usually uses 10 digital pin slots on its own, I was able to run it in reduced rate mode, which only used 6 digital pin slots. The remaining slots are taken up by the ultrasonic sensor, which used 2, and the passive buzzer, DC fan, and temperature and humidity sensor, which each used a single digital pin. The sole analog pin was used by the gas sensor. The setup of the code was divided into 3 main sections. First, the library calls, pin definitions, and sensor type definitions. Second, we define some constants, gamma and R for air, the threshold above which the gas sensor will be triggered, the distance between the ultrasonic sensor and the wall, and a timer so that we can shut off the fan after a few seconds once gas is detected. The actual setup function is very simple. First, we initiate serial communication, although it's not necessary for this device. Then we initiate the sensors and set the pins to the correct output mode. At the beginning of every loop function, the code checks whether the measurement from the gas sensor is over the threshold defined earlier, or whether the temperature sensor detects an ambient air temperature of over 100 degrees Celsius. If so, then it activates the fan and the buzzer, and gives a warning in the serial monitor. If everything is nominal and safe for operation, we then check the fan timer to see if there's any time left for the fan to run. Then we move on to looking at the temperature from the temperature sensor, which we plug into the square root gamma RT equation to get our predicted speed of sound. Then we record half the time of the ultrasonic sensor because it has to travel to the wall and back, so we need to account for that. And then we get the measured speed of sound by simply dividing the distance by the time, with that 1 million in there to account for the fact that the time is in microseconds. Finally, we display the result on the liquid crystal display and wait for 600 milliseconds before taking another measurement. Now let's see the results. Thank you for watching my presentation.